Hi there. So we will just start with the second lecture. Let me just go here. So in the last lecture, we started talking about learning augmented algorithms, and we gave an example of binary search where we saw that okay, learning augmented algorithms can beat worst case bounds, right? And in this lecture, we will see one learning augmented algorithms for k-means, right? So I will first introduce to you what k-means is. I will give you a general algorithm for k-means, which is the Lloyd's algorithm, and then we will have a learning augmented algorithm for k-means and we'll analyze it. Okay, this is what we'll do in this lecture. Okay, so let's start. So suppose you are to start with an example. Suppose you are given a bunch of points, right? So these are the points that is given to you, and assume k is given to you as 2. That means you need to find two clusters with respect to these points. So what would be one of the clusters? One of the clusters could be this one, and the other cluster could be this one. In this case, if you just see the data, it is visible that okay, these two could be the clusters, right? But and coming up with such kind of algorithms for k-means is that you find, given this set of points you find, and given k you find that number of clusters, right? Suppose for this case this is the optimal cluster, but you might not end up with optimal cluster just because k-means is in np complete, np hard, because the problem involves a computatorial search over all possible partition of the data points into k clusters, right? So let us just formally define this problem and then see. So you are given a bunch of points. Okay, so you're given a point x1, x2, dot xn, right? And you might have initial k centers or centroid. Suppose c1, c2, ck, right? And your task is to minimize the within cluster sum of squares. So what is the cost function that you want to minimize? Is cost of this. So this is denoted as x. So cost of x on c is written as summation all x belongs to x. You want to minimize with respect to c belongs to capital C, the Euclidean distance. Okay. Where what this term basically means, suppose if your E is x1, y1 and your C is x2, y2, then this quantity basically it means that I want to do x2 minus x1 square plus y2 minus y1 square root is 1. And when you square it, this term goes, the square root goes away. So this is the quantity that we want to minimize over all uh, points, right? So how the so for this problem, we'll first give you an algorithm of Lloyd's. So let me just give you the intuition of the Lloyd's algorithm first. So suppose you have this endpoints which are here, right? These endpoints are given here. What Lloyd's algorithm does that in the initial step, it randomly assume that k to be 2. It randomly takes 2 points and consider them as centroid. So let me take just this point and this one. These points are considered as centers. And now what happens is the following: with respect to every point calculates its distance with respect to this kind of cost function with this center as well as this center. Okay. If k is greater than 2, then they will calculate with respect to other centers also. And for whichever centroid the distance is the less, the point is being assigned to that centroid. Suppose in this case it is assigned to this center, this case it is assigned to this center, this point is assigned to this center, and so on, right? So after each and every point is assigned, so suppose the assignment looks something like this. So suppose these are one set of points, right? And which are clustered into one, and these are different set of points. So these are the 2 points. This was in one cluster, this was in one cluster. And now what you do, you take the mean of all these value and find a center. So maybe this would be the center. Again, you take the mean of all these and find a center. Maybe this is the center. And this way you continue until your algorithm converges. And why the algorithm should converge? Just because this cost function is decreasing in every iteration. Okay. So in every iteration, since the cost function is decreasing, the algorithm will be bounded or will terminate in finite number of steps. Okay. So this is the basic uh, algorithm of k-means, also known as Lloyd's algorithm. And now we'll get the algorithm in form. Okay. So let's start. So what is given to you is a set of points, which is x, and you're also, what is your first step? So your first step is you are given an initial set of k-means or k-means centroid. Suppose you are given m1, 1, 2, mk1. This can be initially random also. What is m11? So m11 is a centroid of some cluster 1, and this superscript 1 denotes that this is the first iteration. This is in the first iteration. Okay. This is initially given to you, and now there are 2 steps. In the first step, what we do, you assign points to one of the center. This is our assignment step, right? So in the assignment step, at time t, what you do, you take each of the points, you find for which point, this point, which is the center for which this quantity is minimized over all other center points, right? So you do this thing in iteration t. For all j belongs to k. Okay. So you find an I for which this quantity is minimized, then this xp would belong to that cluster. So you do this for all cluster. And once you're done, you've assigned each and every point to a specific cluster. Now you recalculate the cluster center, which is you want to do an update now. Just you just see what is the cardinality of this. Just you're just doing the average. And you do the average. Okay? And you keep repeating this process until this algorithm converges. Okay? So the running time of this algorithm is, so you have to do this for all the points, right, with respect to every cluster in each dimension. And suppose the algorithm terminates after I iteration, then your running time is order mktr, right? So we are assuming here that the points in X belongs to RT. So this is the running time that you will get. So this is just the simple Lloyd's algorithm, and it works very well in practice, right? People use them a lot, right? But the time complexity is very high of this algorithm, right? And again, as we discussed in the last lecture, what we want is, since we have this data and lots of data that we have, we want to incorporate this data in our algorithm design, right, to get a better one. So now we'll see that how can we do that, right? Okay. So now what we want to do is that we want to design a learning augmented algorithm for this case. Why we want to design a learning augmented algorithm? To get a better bound? Just because, again, as stated earlier, this problem is NP hard. It is even NP hard to approximate it within a factor of 1.07. Okay. And since we have lots and lots of data, we want to use prediction to get better bounds. Okay. So the paper that we're talking about right now would be a paper called Learning Augmented Kmeans Clustering by Ergun et al. This is in ICLR 23. We will be discussing this paper. Okay, that what they have done. So let me set the initial goals that we want to achieve. Again, the goal is the same. We have bunch of points, and for simplicity, I will denote the notation the as it is denoted in this paper, so that there is no confusion if you just go and read this paper again. So we'll denote the points as P and center as C. So our cost function is exactly still the same. So this is our cost function that we want to minimize. So for each point belongs to P, and for each center belongs to C, we want to minimize P, where each point is in P is in RT. So apart from the points and the center, since this is a learning augmented algorithm, the extra information that we have now is a prediction also. So we have a predictor pi. So what is this prediction? So this predictor pi gives us a prediction for each of the points as label. So for each point in your data set, you will get a prediction. So since suppose assume we want to do k clustering, so you will get a label between 1 to k, which will denote that the point is saying that I belong to this cluster. So if suppose this point cluster is prediction is J, prediction level is J, then it just says that the prediction is that I belong to the cluster J. If this point's prediction is 2, then it just says that I belong to the cluster 2. So these are the predictions that is given to you. This prediction might be correct, this prediction might be wrong. Okay. So what they have done in this paper is that they have bounded the wrong number of prediction that can come to you. So let's see how. So from where we are generating this pi? So this pi is being generated from some 1 plus alpha approximate solution. Okay. So you have some solution. So suppose there is an 1 plus alpha approximate solution that you already know about. You take that solution and you treat this solution as your predictions, right? And you go forward. And what is one more thing here? So one more thing is something called label error rate, which is some lambda which is less than this alpha. What it says is that it says the following. Suppose these are the points that is labeled by my predictor pi as I, right? Then at most alpha, suppose the number of points here is mi, so only alpha mi of them can be mislabeled. Okay? Mislabeled means, so suppose all these points were considered to be labeled I, but suppose there is a point here, right? In the optimum, it belongs to some other cluster, but it is also labeled I here. Maybe this point also is labeled I. It belongs to some other cluster. So at most, alpha of them can be wrong. Okay? So this is the condition that they have. So if a cluster has total mi points, alpha mi of them would might be mislabeled. Maybe less than that. In general, it is lambda. Okay. So this is the setup that we have. And with this setup, what we want to prove, the result that we want to prove is the following kind of result. Again, this is informal. I will define the exact theorem when we are there. But what we want to show is the following, that let C dash be the center output of the algorithm that we will discuss. Okay. Then cost of P on this C dash given alpha, lambda, and pi as the prediction is 1 plus order alpha times cost of the optimal solution. C of where C of is the optimal k-means clustering. And this will do in order k and d time. Okay. Where it should be here. This side is a log factor. Okay. So by just looking at this result, you might think that given a predictor which is like 1 plus alpha approximate, it might be easy to just go with the predictor, that whatever the clustering that is defined for the predictor, I just take that and I just recalculate the center and I will get a 1 plus order alpha kind of approximation. I don't why I have to come up with a new algorithm, right? You just follow the predictions, right? But okay, let me just give you an example. Just following the prediction is not enough. Suppose these are the points that is given to you, and there is a point which is here, which is a bit far from all these points, and all these points are labeled I. Okay, so each of these points are labeled I, and I assume this is a wrong prediction, right? Then if you just calculate the mean with respect to all these points, your mean might shift to somewhere here now, right? Because of this mislabeled one point, right? And if this point is very, very far away, this one point can increase your cost function by a lot, right? It might be unbounded, right? So what we want to do is that, okay, we want to just find the average, we want to just find the mean of this point, but at the same time, we want to get rid of this kind of bad outliers. If we don't have this kind of bad outliers, so even if here we have some points which are mislabeled, suppose these points are mislabeled, even in that case, we'll get a clustering which is pretty close, maybe a clustering which is here, right? So in that case, maybe we can say that this is like 1 plus order alpha bound. Right? So the main task of the algorithm is to get rid of these outliers first, right? And once you get rid of these outliers, then you calculate the mean, and then we'll show it is like 1 plus order alpha. In general, what we'll show is that this is actually 1 plus 20 alpha. Okay. So this is what we want to show. So just using the prediction and just going with the prediction is not enough. Okay. I hope this is clear and the setting is clear. So let's just start with by just giving the algorithm itself. Let's start. Let's with the algorithm. So what we have as input are point set x with labels given by pi, and we know there is some label error rate of lambda which is bounded by alpha. And what we want as output is 1 plus order alpha approximation. Right? So what we'll do is the following. For each of the cluster, so for each of the labels which are labeled I by my predictor, I go to that level. So first I go to level 1, which were predicted by my cluster. I take all the points and I say them that they are for label I. I denote them as yi, be the set of points with label I. So I take all these points, and we know that these points are in d dimension, they are in Rd. I run another algorithm called coordinate estimate for each of these points, for each of the d coordinates of these points. D coordinates of yi. Okay. And once I have done with this, I will get a approximate center ci dash. Okay. And I will this would give me output as ci dash. This is where my for ends, and for all I will do this, and in last what I will do is just return c1 dash to ck dash. So what this algorithm is doing is the following. It is going to a particular cluster which is labeled I. We know that all these points are in d dimension. It takes one. It just projects one dimension of each of the points. It gives to an algorithm called credit estimate. With respect to that dimension, credit estimate would give a mean point or a center point. We do this for all dimension. What we end up is ci dash. Okay, and we do this for all i's. What we end up is a clustering ca1 dash to ck dash. So this is the clustering that would be returned by this algorithm. And what is a credit estimate algorithm? Let's see. So in the coordinate estimate algorithm, what we have as an input are points x1, x2 to x2m, and all this belongs to R because it is projecting one dimension here. So the algorithm goes like this, that from these 2m points, we just randomly partition them, okay, into two equal set of x1 and x2. So one set is denoted as x1 and the other set is denoted x2. Just randomly partition them of size. So both of this set has size n. Now what you do, you just find an interval. So let I a to b is an interval of this one like a shortest interval such that it contains m into 1 minus 5 alpha points of x1. Okay, so I'll explain this while, and then you find that what are the intersecting points with respect to these intervals on the set x2, and then you just whatever you've got there as an intersection, you denote this the points as set, and then you return small set, which is the average of all the points which belongs to set. Okay, and you just return It just returns it. So what this great estimate algorithm is doing is the following. So we have since we projected our point from one of the dimension, and now we have two endpoints. We randomly divide them into two sets. Suppose this is one of my set, this is x1, and this is my other set, which is x2. I go to x1, I take the shortest interval that contains 1 minus 5 alpha points. That means I'm taking an interval which is short, but at the same time it contains a lot of points, right? And since it contains a lot of points, it is guaranteed that some of these points are actually true points. Now, whatever this interval is, I just project the same interval into x2, and these are the points that are there in my set. I take the average of that set and return this as my center point for this dimension. And let's do this for all dimensions. And what our claim is that this is a pretty good approximation of the true points or the true clustering. Okay. So this is what the algorithm is. So by doing this, what in somehow what you're doing is that you are just getting rid of as many outliers as possible. Just because you have the shortest interval, and in this interval the points are very much concentrated. So if something, so in this case, this bad outlier that we show earlier, it might be the case that that bad outlier would be omitted. But we have to prove this, right? So now we'll prove this algorithm. So let's start proving this algorithm. I hope everything is clear till now. Okay, so let me just write here lemma 1. Okay, the numbering might be different from the original numbering that is given in the paper. Okay, so suppose let PQ be subset of R be the set of points on the real line, okay, such that finality of P is greater than 1 minus alpha times N, and finality of Q is bounded by alpha times N, where N is, so X is P union Q, and X N is the cardinality of X. Okay. Let CP be the mean of P, CX be the mean of X. Okay. Then the cost of X on CP is 1 plus alpha by 1 minus alpha square cost of X on CX. Right? So we want to prove this lemma. So what this lemma actually says is the following, that for X, CX is the optimal mean or the optimal cluster point, right? And CX, CP is some approximate point, right? Because it contains a lot of points, but it's like 1 minus alpha endpoint it contains. So if I just take, with respect to X, if I just take CP to be my mean, then I can show that, okay, I am not very far away from the optimal mean or from the optimal cost, right? It is just 1 plus alpha by 1 minus alpha square factor away. So let's prove this thing. Okay, so suppose without loss of generality that C of x is 0, okay, Cp is less than 0, then C of q is greater than or equals to 0. Okay? And now we apply a famous lemma that cost of x on Cp is just cost of x on Cx plus the cardinality of x and Cp minus 6. This is by Inaba et al. Okay. So just by looking at this lemma, you can see that to prove the above lemma, what we have to show is that this quantity is bounded by alpha 1 minus alpha whole square cost of x6, right? So if we just prove this, we are done. So let's prove this thing. So as we know that Cx is 0, then P into Cp equals minus Q into Cq, okay? And let the exact cardinality of P to be 1 minus delta times N. So the exact cardinality of Q is just delta times N, where this delta is bounded by alpha. Then from the above equation, Cq can be written as this, and if we just plug in, we can just write this as this. Okay. And now, as the cost of Q on Cx is greater than the cardinality of Q into Cqx, if we just plug in the details, we know that this to be 1 minus delta square Cp square, and if we just plug Q to be n delta, we'll have n 1 minus delta square by delta square Cp square, right? So this is what we will have. So it should be delta here, and we just plug in lamp. So these are all equal to plug in alpha. Then this is just greater than equal to n into 1 minus alpha square by alpha Cp square, right? And now what we wanted to prove was let's calculate this quantity. So as Cx is 0, this is nothing but this, and this can be derived from the above equation. So we can write this as alpha n into 1 minus alpha square cost of q on Cx, but cost of q on Cx can be bounded by alpha n into 1 minus alpha square cost of x on Cx, right? And to prove the above lemma, we can see that here we also have an x here. So the cardinality of x is n. So if we just plug n here, so if we just plug it n here, so this n and this n will get cancelled and we will get our lemma, right? So this is the proof that there, if we just go and take some approximate solution, it is in the original setting, it is a very good, it will give a very good approximate solution, right? It is like 1 plus alpha by 1 minus alpha square sub. I hope this is clear. So let's see. Okay, let's start proving something more. So initially we talked that in the above uh, lemma, sorry, in the above theorem, there was this interval I, right? So let's talk something more about that interval I. Just check the microphone properly here. Okay. So now we'll show that an interval I star, this is not exactly I star with small length can contain a lot of true points. Okay, so this is what we want to show. So let's name this as lemma 2. So what we want to show is for a fixed set X subset of R, let C be the mean of X and sigma square is the variance. Let this be the variance. Okay. Then there is an interval I star which is like C minus sigma C plus sigma by root alpha that contains at least 1 minus 4 alpha fraction points of X. Okay, so that means this interval contains actually a lot of points. So let's prove this thing. So how this proof, so how this interval I is looking, so C is here, C minus this quantity is here, and C plus this quantity is here. Right? So this is the interval that we have for, this is the I star interval, right? It would look something like this. So take any point small x belongs to x minus I. So any point which does not belong to this interval. So this point would satisfy that the distance from this point to C square is greater than this. Okay. And now if more than 4 alpha fraction of point small x, so like if more than 4 alpha, if there are more than 4 alpha fraction of points such that they don't lie in this interval I star, then what we can show is that the total variance is larger than sigma square, which is a contradiction. So number of points which could be outside this interval can be at most 4 alpha. So that means within this interval there are at least 1 minus 4 alpha number of points. Why you just take, suppose that the number of point outside this interval is 8 alpha, then you'll end up having the total variance to be 2 sigma square, right? Which is a contradiction. So what we have shown that there is some interval I star for which if we just take that interval, so there are many points that are there in that interval. But this is not exactly the interval that we were considering earlier, right? Our interval was I. So let's now give some bound on I itself. Okay. So what will show is that the interval I has small length than I star with high probability, yet I also contains a lot of true points. Okay, so this is what we want to show. So let give this name as lemma 3. So let m be a sufficiently large constant. Okay, then there is an interval I a to b that contains at least 1 minus 6 alpha fraction points of x2 and such that b minus a is bounded by 2 sigma by root alpha. This is smaller than I star, right? So because I star is 2 alphas. This is with high probability. With high probability. Okay. So you want to prove this line that the interval that we considered earlier, that interval has a lot of points in it. Okay. At least 1 minus 6 alpha number of points of x2. Okay. Let's prove this thing. So suppose we have a set of 2m points that we similar to the grade estimate algorithm that we partition into randomly partition into x1 and x2. Okay. Now consider an interval j that have at least 2 cm points where c is greater than 1 minus 5 alpha. Again, this is just because the grade estimate algorithm had 1 minus 5 alpha number of points. So let J1 and J2 be the number of points in J that are in x1 and x2 respectively. So J1 is a number of points which in J which is also there in x1. So J1 is just J intersection x1 and J2 is just J intersection x2. Then by Chernoff bound, so by Chernoff, we have that both J1 and J2 are at least MC1 minus alpha with high probability. Right? This is just by Chernoff bound. Then cardinality of J1 minus J2 is bounded by alpha MC with high probability. Why? Just because you take one of them to be MC1 minus alpha, and we know that the total number of points in J is 2MC. You just subtract them, you'll get this J minus J2 to be bounded by alpha MC, right? So as I contains at least m into 1 minus 5 alpha fraction points of x1 and j1 minus j2 finality is at least alpha MC, I must also contain m into 1 minus 6 alpha fraction points of x2, right? Just because you just subtract them, you'll get m into 1 minus 6 alpha, at least this many points of x2, right? So we have proved this lemma. Okay, I hope this thing is clear. And now with all these three lemmas in hand, and let's assume a small lemma that, let's call it lemma 4, which is like, let S be a set of points obtained independently by sampling each point of X subset of R with probability half. Okay, let C be the center, be the, you can say, the optimal center, optimal center of X, and CS be the center of S. Then probability that the cost of X on CS is greater than 1 plus alpha cost of X on C is very, very less. Now this is greater than, so this probability is very less. The probability that you take uh, XCH to be your center and you find the cost and this would be greater than 1 minus alpha is less. So we assume this lemma to prove our main theorem now. Okay, so the main theorem that we want to prove is the following. Let's add one more page. Yeah. We want to prove this following theorem that let alpha belongs to 10 log n by root 10 and 1 by 7. Let P comma Q be subset of R be the set of points on this real line such that cardinality of P is greater than 1 minus alpha times 2n and cardinality of Q is bounded by 2 alpha n and X equals P union Q. Right? Let C be the center of P. Then the algorithm grade estimate on input point X and a point C dash, which is like the output of grade estimate. The cost of P on C dash is bounded by 1 plus 18 alpha, 1 plus alpha, 1 plus alpha by 1 minus alpha whole square cost of P on C. This one we want to. If we just simplify this, we will get this to be 1 plus 20 alpha. Okay. So this is the lemma or the main theorem that we want to prove. We have now all the machineries in hand now to prove this lemma. So we just prove this theorem right now. So let's start. So proof. So as alpha belongs to 10 log n root 10 and 1 by 7, okay, then by lemma, at least I think the third lemma, by the third lemma we have that I intersection X contains at least 1 minus 6 alpha m points of P intersection x2 and 2 alpha m points of Q in the interval length to sigma by root alpha, where alpha square is what we have defined before, right? Then, so this is what we already know. Then from the first lemma, okay, so from lemma 1, what we know is cost of P on C0 is 1 plus alpha by 1 minus alpha square. Cost of P on C1, where C0 is the center of I intersection P intersection x2 and C1 is the center of P intersection x2, right? Again, from lemma 4, we know that cost of P on C1 is bounded by 1 plus alpha times cost of P on C with high probability. Right? So this is also what we know, right? Again, as C0 is the center of I intersection P intersection x2 and C dash is the center of I intersection x2, what we have is I intersection P intersection x2 cardinality into C0 plus summation Q, where Q belongs to I intersection Q intersection x2. This should be equals to I intersection x2 into cardinality of C dash, right? And as we know that the length of I is 2 alpha to sigma by root alpha, right? And taking alpha to be very small such that this quantity C dash minus C0, this is bounded by 6 root alpha into sigma, right? We get our result as follows. So we know that cost of P on C dash is cost of P on C0 plus cardinality of P into C0 minus C dash square. This is just by Inaba. Then this can be written as cost of P on C0 plus cardinality of P. We know that C0 minus C dash is 6 uh, alpha root alpha into this. Then we'll get square it to be 36 alpha sigma square. Putting the value of sigma there, cost of P on C0. So this is P, this is 36 alpha, sigma is 1 plus 2, cardinality of P, cost of P on C. So this and this get cancelled, we get 18 here, P and P gets cancelled. So this gives us cost of P on C0 plus 18 alpha cost of P on C, right? And together with the other places using lemma 4's cost and lemma 1's cost. If we just take everything together, what we get is cost of P on C dash is bounded by 1 plus 18 alpha, 1 plus alpha, 1 minus 1 plus alpha by 1 minus alpha whole square cost of P on C, which is just like 1 plus 20 cost of P on C. So this gives us our desired theorem, right? And with this theorem ends here. So what we have shown is that in general, that you start with some prediction. You you remove the outliers and you take that prediction to take the average in each dimension and return that as your cluster centers, and you calculate a clustering ratio to that cluster center, then you're not very far away from the optimal cluster, right? So this is what we have, and this is what they prove in their paper. So yeah, this lecture is all about it. In the next lecture, we'll again see a similar algorithm where the setup is the same for k-means, but that has some improved results. Okay, so we'll just see that in the next lecture. Thank you. I'll stop here.